In this video, we specify the net's mechanisms for creating a safe, not just safer, transportation system. The mechanisms we describe would make the likelihood of any collision involving a moving nets vehicle in any given year close to zero. That is largely obtained by eliminating most potential collision causes and ensuring a fail-safe response if a potential collision were to arise. Nets has a mode we call WAN, for Wide Area Network, which uses elevated, covered, and multi-track guideways with only 3D crossings and intersections. WAN vehicles are fully automated and move suspended beneath the tracks. There are many suspended vehicle systems, like the Schweeb one shown here. WAN vehicles are larger than Schweeb ones, accommodating 2 large adult passengers comfortably, or carrying similar sizes or masses of goods. The other features make for trivial automation requirements. As we show soon, these features eliminate all collision causes other than natural disasters. The impact of those is reduced to near zero. It is this small size and mass that enables all of the other noted WAN characteristics and their safety benefits. The guideways mostly run along the rights-of-way of Cut's major roads, including expressways and arterial roads. On this map of central Ontario in Canada, all the roads shown would have 1 bidirectional or 2 one-way WAN guideways on opposite sides of the road, or a combination of these along some expressways. The WAN guideways partition the landmass into nets neighborhoods. Neighborhoods are the smallest areas bounded by WAN routes and natural obstacles like a lakeshore or river. For trip legs within neighborhoods, or for single items that do not fit in WAN vehicles, the net's LAN mode for local area network is used. We will describe LAN soon. WAN handles all travel between the initial and final neighborhoods, making up the bulk of all but the shortest trips. As we zoom into Toronto, note that the major streets and the corresponding WAN guideways are more tightly spaced, meaning smaller neighborhoods. We zoom further to the neighborhood northwest of the Yonge Finch intersection. We start by focusing on that intersection to illustrate the WAN mechanisms and attributes and how these eliminate the causes of collisions. The WAN guideways that bound the neighborhood are the blue paths here. There are 5-track WAN guideways on either side of Yonge Street and Finch Street. The multiple tracks are there mostly for trip time reasons. The bottom of moving vehicles is above the point reachable by any object moving on the ground in the area. That is typically about 4 to 5 meters above ground level. There is then no chance of such an object accidentally colliding with a moving WAN vehicle. That is independent of whether the collision cause would be actions performed by that third party or the vehicle controller. Most WAN intersections operate like expressway cloverleaf intersections. All left turns are implemented as 3 right turns. The actual right turns occur at the intersection and are not shown. Unlike in expressways, the left turn tracks do not need to occur inside the intersection, but can extend, as here, along any nearby street or across a parking lot. Like on expressways, the 3D crossings and intersections allow through traffic to safely cross without even slowing down. Turns at intersections then just require track switches, which are easy to automate safely, given detailed knowledge about the guideway and all nearby vehicle track positions and speeds. This applies at all points along the tracks. The result is that automation is easy, and that automation eliminates driver errors as causes of vehicle-vehicle collisions. The covers and other mechanisms provide isolation from flying objects. The covers also provide isolation from weather effects that cause collisions involving Cut's vehicles. These effects include various forms of precipitation and high winds. Aggressive vehicle and guideway monitoring and preventive maintenance mechanisms eliminates the potential for wear-related mechanical failures as a collision cause. The French and Japanese high-speed rail systems have suffered no fatalities during billions of passenger trips over decades along their high-speed guideway segments. That is a result of physically isolated tracked guideways with no 2D crossings or intersections. The physical isolation uses ditches, fences, or raised earthen viaducts. These obstruct ground traffic crossing the guideway, but otherwise are analogs to WAN's elevated guideways. The tracks and lack of 2D crossings or intersections provide similar benefits to both. However, the very large spatially shared trains create cost and trip time issues avoided by WAN. Note that it is the provision of the physically isolated tracked guideway with only 2D crossings that enables the high speeds achieved by the bullet trains. As we shall see in our trip time discussion, WAN exploits its implementation of those properties to provide similar top-end speeds. We now focus on the neighborhood northwest of this intersection to provide an example to demonstrate LAN. But before that, we specify the WAN vehicle loading and unloading mechanisms that occur before and after every WAN leg, respectively. One of the tracks on these WAN guideways is only used for vehicles to stop and load or unload their cargo. We refer to any location on these tracks as loops, standing for loading or unloading points. The CUTS loops include things like parking spots, bus stops, and boarding gates. WAN loops occur anywhere along the loop track. On average, these would be at least as frequent as every 20 meters along the loop tracks. As illustrated, the bottom of the vehicle descends to perform the loading and unloading of its cargo. Each vehicle can be configured to carry passengers with provided seats or in something like a powered wheelchair. Another configuration would carry goods. The goods must be inside NETS boxes that are designed to allow automated handling by the NETS vehicles. NETS legs within neighborhoods are provided by the LAN, standing for Local Area Network, mode. The LAN vehicles for people are basically electrically powered, wirelessly communicating, and automated versions of today's scooters, skateboards, bikes, trikes, and wheelchairs. The initial LAN leg, typical for one passenger within a neighborhood, is illustrated now. When the departure point or arrival point for the trip is near enough to the neighborhood boundary, passengers may often choose to walk or use a personal vehicle like a wheelchair. Goods are moved exclusively in NETS boxes carried by different but still small and light LAN vehicles. Multiple of these may pull larger trailers to move boxes that do not fit inside WAN vehicles. LAN vehicles would initially travel along existing CUTS roads, sidewalks, or some walking or cycling paths. Over time, the roads may be removed if there is no longer CUTS traffic within the neighborhood. LAN vehicles are fully automated and in constant contact with nearby LAN vehicles and a set of stationary wide-spectrum sensors. The sensors detect moving objects like other LAN or CUTS vehicles, pedestrians, cyclists, or land animals as soon as they enter the line of sight of the sensors. They are also aware of any currently stationary object that has moved in the recent past. The sensors have 360-degree views of their surroundings. LAN inter-vehicle communications are sufficient to ensure no LAN vehicle-vehicle collisions. As soon as a potential trajectory collision is detected, it is avoided by having one or both of the vehicles change to a non-intersecting trajectory. The sensor network ensures that vehicles are aware of any object moving along their path within milliseconds of when the object enters the line of sight of the sensor. Vehicle third-party collisions are then avoided as long as the vehicle can adjust its speed or path before the trajectories intersect. The LAN vehicle speed along any segment is set to ensure that the vehicle can perform an emergency braking as soon as the sensors detect a potential collision. A 10 meter per second vehicle braking at 0.7 G, which is the top of the range for the current e-bikes, would be stopped within about 7 meters. The distance from the building doors on our sample trip to the center of the streets, where the LAN vehicles would move, is about 10 meters. A pedestrian emerging from a door would take longer to reach the center of the street than it would take the vehicle to stop. At 10 meters per second, our sample LAN leg would take 36 seconds. This philosophy, adjusted according to weather conditions and cargo type, size, mass, and any knowledge the system has about the location of mobile third parties, would ensure a moving WAN vehicle would not collide with any such parties. The CUTS autonomous vehicle efforts also eliminate human error in the control of the equipped vehicles. They also provide quicker response to potential collisions as soon as they are detected. However, detection is constrained to events that are visible to the onboard vehicle sensors. The large size and mass of the CUTS vehicles also makes for large stopping distance once detection occurs. These factors limit the ability to avoid collisions caused by pedestrians, cyclists, animals, and any remaining human-controlled CUTS vehicles. LAN addresses all those limitations of the CUTS autonomous vehicle efforts. In summary, LAN and WAN are able to avoid all vehicle-vehicle and vehicle third-party collisions. This is not just a quantitative but a qualitative difference with CUTS. No longer will children need to learn to be safe in traffic. NETS is a transportation system that has learned to be safe for its riders as well as all third parties. CUTS high-speed rail systems understand one way to do it via physically isolated tracked guideways with no on-grade crossings or intersections. but the cost and operational restrictions of that solution make it applicable to only a small fraction of trips. Those limitations arise entirely from a flawed initial assumption that large and heavy or huge spatially shared vehicles are required to service the trip demand. The amount of data that is available to nets from all its sensors could present serious privacy issues. In one of the videos linked at the end, we present how nets would provide both strong privacy and enhanced security. The other link is to the trips time video where we show that, like CUT's high-speed rail systems, WAN guideways support high speeds through eliminating stops at crossings and physical isolation from third parties and other vehicles that avoids the need for safety-motivated speed limits. We have already seen here the hints of the 24/7 on-demand trips with sub-minute response times.